Hello, my name is Lucia and I am a geologist with the Nevada Division of Minerals. Understanding climate change. I hope you saw the fine print when you read the title of this presentation. Climate change is complex, and you will not walk away from here today a master of climate change. I volunteered to teach this class at one of our biannual Earth Science Teachers Workshops, hoping to bring to light global temperature fluctuations along with the complexities associated with climate change using some significant events from Earth's 4.6 billion year past. It was extremely interesting to research and learn about this topic for me. I hope you will feel the same. During this presentation, we will review greenhouse gases, historic global temperatures, the geologic timescale, snowball Earth, the late Devonian extinction, the end Permian extinction, our current ice age, the Toba catastrophe, and climate change variables. Greenhouse gases. They are important, and we do need them in moderation. The four main greenhouse gases are carbon dioxide, methane, nitrous oxide, and fluorinated gases. Currently in geologic time, these gases are sourced from both human and natural activities. Household and commercial combustion of fossil fuels, solid and organic waste treatment and decay, and use of fluorinated gases for things like refrigerants are some of the human sources for greenhouse gases. Natural sources for greenhouse gases include volcanic activity, organic decay, and the natural release of methane reservoirs. This is a geologic timescale representing the last 850 million years of Earth's history. The red area represents time spans that Earth has been in a greenhouse state, or what scientists call greenhouse Earth. The blue represents colder, icehouse Earth time intervals. The key takeaway here is that 3/4 of the last 850 million years, Earth has been in a greenhouse state. For clarification, according to scientists, an ice age is defined as whenever extensive ice sheets are present in both the northern and southern hemispheres. Also shown on the screen are the big 5 extinction events that have been documented during the Earth's past, along with a period of time referred to as snowball Earth. The events in bold will be the ones discussed during this presentation. I would like to offer some perspective on geologic time before we move on. Here we have the geologic time scale, or the 4.6 billion years of Earth's history put to the calendar year. Each time period is shown by a different background. So the first period of time is the Hadean, and it is represented by the lava-looking background covering the whole month of January and just over half of February. Using our calendar, the formation of the Earth occurred on January 1st. The inferred origin of life, or the first cells, on February 25th. The first ice age Earth ever experienced, the Pongola Ice Age, March 29th. Cells with a nucleus. These are the types of cells you have. Don't show up until July 18th. Around this same time, the Huron Ice Age begins, which is the second ice age to affect planet Earth. October 11th marks the beginning of snowball Earth, which lasted all the way until the end of the day on November 18th. This was followed by the Cambrian explosion of life. This is when multicellular life really grabbed hold and began to take off. The first fish on November 21st. The third ice age, the Andean-Saharan Ice Age, begins early on November 27th, followed by the first land plants, which appear later that day. The late Devonian extinction took place towards the end of the day on November 30th. Sharks and land animals show up in the fossil record on December 2nd, followed closely by the Karoo Ice Age, which began on December 3rd. Reptiles make their debut on December 5th. The first mammal-like reptiles appear on December 11th. The biggest extinction event the Earth has ever experienced, the Permian extinction, which we will discuss, took place midday on December 12th. First dinosaurs, December 13th. First mammals, December 14th. First birds, December 19th. First flowering plants, December 22nd. T-Rex doesn't hit the scene until December 26th. The late Cenozoic Ice Age starts during the last half of the day on the last day of the year. Modern humans don't show up in the fossil record until the last 12 seconds of the year. Out of 31,536,000 seconds that make up a year, we represent just 12 seconds of that. Let's get started. We will begin with the Neoproterozoic snowball Earth. Around 3.4 billion years ago, around May 21st on our calendar, early single-celled organisms had evolved to the point where they had developed the ability to photosynthesize. Photosynthesis is where an organism uses sunlight while consuming carbon dioxide and water to produce oxygen and glucose. These photosynthetic organisms were cyanobacteria. Through the photosynthetic process, cyanobacteria would introduce oxygen into the paleoatmosphere. This may not seem like a big deal, but it was rather significant as there was no atmospheric oxygen up to this point. In fact, there was no oxygen at all. It was all tied up with hydrogen in the form of water. At the beginning of the Neoproterozoic, around October 11th, oxygen levels had increased significantly in the atmosphere. The excited atomic oxygen reacted with water, forming hydroxyl radicals, which oxidize atmospheric methane, converting it to CO2. This process decreases the methane concentration in the atmosphere and increases the atmospheric water and CO2 concentrations. Methane traps 84 times more heat per mass unit than carbon dioxide, so carbon dioxide is preferential to methane. But without enough methane, the Earth will cool, and that's exactly what happened. As temperatures fell, glaciers began to form. Since glaciers and snow are white, they are highly reflective of solar rays, so their presence increases the Earth's albedo, or the fraction of light, heat, the Earth can reflect. As heat was reflected, it got even colder, causing the glaciers to get bigger, further increasing the albedo, causing the glaciers to get bigger. You see where I'm going here. Snowball Earth would last for 120 million years, or until the end of the day on November 18th. This is the longest lasting, most extensive ice age Earth has ever experienced. If water is locked up as ice, then erosional processes slow way down. As erosion takes place, the release of alkaline metal ions such as beryllium, magnesium, calcium, strontium, barium, and radium from siliceous rocks withdraws CO2 from the atmosphere. Cold temperatures would also decrease populations of photosynthetic organisms. So for the duration of snowball Earth, CO2 consumption from weathering, erosion, and photosynthesis was at a minimum. And any CO2 that was being released into the atmosphere would simply accumulate, which ended up being a really good thing. And that's what scientists believe happened. Ongoing volcanic activity and oxygen-consuming organisms would come to the Earth's rescue. Due to decreased rates of CO2 consumption, CO2 would accumulate in the atmosphere along with other greenhouse gases such as sulfur dioxide derived from ongoing volcanic activity. As the greenhouse gases accumulated, temperatures would begin to rise. As temperatures rose, the ice would begin to melt, releasing any trapped greenhouse gases like methane. Atmospheric methane levels would increase, causing temperatures to rise even more. This would melt even more ice, and eventually Snowball Earth was gone, a thing of the past, forgotten. Well, it would have been if it wasn't for us rock-loving, meddling geologists. This would bring the Earth back into a greenhouse state of being. Moving on to the Devonian extinction, we will call it December 1st or 2nd. This is the second major extinction event to occur on planet Earth. The exact time span of this event is uncertain, and the exact cause is difficult to pin down due to the duration of the extinction. For this presentation, we will be focusing on weathering, anoxia, and global cooling as it relates to this extinction. During the late Devonian, plants had fully transitioned to land and now included large lycopsids, sphenophytes, and progymnosperm trees. There was also significant tectonic uplift during this period. Newly introduced trees had a much larger root system, which broke up the soil. Coupled with plate tectonics, erosion rates increased significantly. Eroded material would have included soil, organic debris, and rock fragments, which were ultimately transported to the oceans. The incumbent sediment would have negative effects on shallow water biota, accounting for some die-off. But the main killer would be a massive algal bloom. Eroding sediments serve as sort of a multivitamin for algae, especially if in high abundance. The algae feed on the sediment, become all fat and happy, and bloom. Algae blooms can consume much of the available oxygen in the water, making the local water column anoxic. Large algae blooms also block out sunlight necessary for photosynthesis to take place. And lacking the means of making food, the photosynthetic organisms below die off, as does everything that feeds upon them. The blocking out of the sunlight also decreases the temperature of the water, especially in the absence of a new carbon dioxide source. As the organisms in algae die, they take their carbon with them. And if rapid burial occurs due to tectonic uplift, the carbon would become locked up in the lithosphere, aka in the rock, making beds of coal. This would lock up carbon from the carbon cycle, prohibiting it from re-entering into the atmosphere, causing overall temperatures to fall even farther. This new abundance of large vegetation was also pulling additional CO2 out of the atmosphere via photosynthesis. As the carbon dioxide was consumed, temperatures began to fall. As temperatures decreased, glaciers began to form. The Earth's albedo increased due to the increased amount of glaciers, and ocean temperatures began to fall. Cold water absorbs more CO2, so CO2 levels fell even further. This caused global temperatures to fall even further as well. The end Permian extinction, December 12th. If it isn't evident at this point, it will become more obvious within the next couple of slides that factors governing climate change are complex and numerous. There are many variables and many chain reactions that can occur. Sometimes the reactions are so severe they spiral out of control. The end Permian extinction was one of the biggest extinction events the Earth has experienced to date. It set the biological clock back 300 million years, or all the way back to the beginning of the Cambrian, late in the day on November 18th. Scientists believe the extinction event was due to a very large, long-lived volcanic eruption which had several pulses. This would be the eruption of the Siberian Traps, the largest eruption that has occurred in the last 500 million years. The 2 million-year volcanic eruption resulted in an estimated 1 million cubic miles of lava. Carbon dioxide accompanied the lava and was released in large volumes into the atmosphere. As the carbon dioxide accumulated, temperatures started to rise. As things got hotter, ice caps began to melt, and as the ice caps melted, pressure was released on methane reservoirs. This caused the release of methane into the atmosphere as well. This, coupled with the Earth's decreasing albedo, caused even more warming to take place. As more ice caps melted, the Earth's albedo decreased even further and it began to really absorb the rays, causing temperatures to rise, which ensured any ice that was left was melted, which totally decreased the Earth's albedo, ultimately resulting in a hot greenhouse Earth. The temperature rise would kill off many plants, which would in return kill off many animals due to a lack of food, well, along with the heat. Trade wind modification and rising ocean temperatures would cause rainfall to increase, which would be even more severe in nature, causing large floods and large amounts of debris to be eroded off the continent. Eroded material would include the recently deceased, which would be carried out to sea. Again, we have given the ocean a dose of our multivitamin, and a massive algal bloom was soon to follow. The algal bloom would consume large quantities of oxygen, causing anoxia. The continental, oceanic, and algal biomatter would begin to decay, also consuming oxygen, exacerbating the anoxic environment, making it nearly impossible for life to hang on. This, coupled with limited sunlight, would result in the death of many or all organisms living below and slow or stop photosynthesis. This would cause carbon dioxide levels to continue to rise, and in the ocean, this would create yet another problem. Ocean acidification. Limestone is a common rock variety that is made up of calcium carbonate, or the shells, skeletons, and ooze of calcareous sea creatures like corals. If you take any kind of acid, be it vinegar, lemon juice, hydrochloric acid, and drop it on the rock, you will see that it starts to bubble. You are effectively dissolving the rock. The same thing happens when corals and other organisms that use calcium carbonate for their skeletons or shells. Given enough acid and enough time, there would come a point when the skeleton would completely dissolve. Ocean acidification is not a good thing if you happen to be a coral or a shelled creature. Well, let's be honest, not many organisms like and can survive in acidic conditions. So how is ocean acidification achieved? Well, there are two main ways we will look at. As the CO2 from ongoing volcanism accumulates in the atmosphere, it gets absorbed into the ocean. Through a series of complex chemical reactions involving CO2, the hydrogen ion concentration increases, which decreases the pH of the oceans, causing acidification. Calcareous skeletons start to dissolve, and organisms are unable to make their skeletons and die. This will be the same scenario for the other two possible causes of ocean acidification via acid rain we will now discuss. CO2 is not the only gas to be released during volcanism. Let's focus on sulfur dioxide. Sulfur dioxide gas, if present, which it was will accumulate in the atmosphere as well. Sulfur dioxide will bond with water to form acid rain. Right? Not good. The most direct route for acidification of the ocean via acid rain is pretty obvious. Acid rain pouring down on the ocean. The other way is similar to what we saw in the anoxia example, only a bit more sinister. Whatever vegetation may have been left after the initial warming event would be destroyed by the acid rain, as would the topsoil. With most of the remaining plants gone, several more animal species would meet an untimely demise. With the plants out of the way, erosion may now kick into full gear. And with all that acid rain coming down, it will now easily wash all of the acidic material into the oceans, acidifying it even further, killing even more organisms. We have yet another blow taken to the photosynthetic process in the ocean and the ability to fix the ever-increasing CO2 levels from the ongoing volcanism. But wait, there's more. Ozone depletion is all about atmospheric chemistry. Volcanic eruptions have the potential of releasing large volumes of particulates like ash, halogens, and hydrogen chloride into the atmosphere. Scientists have found that particles or aerosols produced by major volcanic eruptions accelerate ozone destruction. Particulates from volcanic emissions do not directly destroy the ozone, but they do provide a surface upon which chemical reactions can take place. This enhances chlorine-driven ozone depletion. So when the ozone is depleted, more radiation penetrates the Earth's surface, which, as we know, has severe and/or fatal effects on living organisms, including plants. We learned earlier that too much oxygen oxidizes methane to CO2. Well, when too much sulfur dioxide is present, it stops or slows the oxidation process from happening, and as a result, methane levels increase as it is no longer being converted to CO2. Remember, methane can hold way more heat than CO2, and with that, the thermostat goes up. So what did we end up with? Remember when we first started discussing the in-Permian extinction? It was stated that there were several pulses of volcanic activity. Some of the events we just looked at occurred more than one time, sending the planet into a serious downward spiral, justifying the reason this event is referred to as the mother of all extinctions. Again, we ended up with a really hot planet with lots of carbon dioxide and only minimal means of sequestering it. Recovery is hard to define. It was geographically specific and numbers range from 1 to 10 million years, as there were some intermittent setbacks along the way. I can hear you asking, well, where did all the CO2 come from? There has been evidence found that the magmas of the Siberian traps intruded into and incorporated coal and other organic material, which according to researchers would account for the high CO2, sulfuric acid, and acid rain along with ozone-destroying halocarbons. So what about our current ice age? Yes, I said current. Well, it began during the last half of the day on December 31st and resulted from the configuration of tectonic plates. This caused a very cold current to start circling Antarctica, which caused temperatures to fall, which caused ice to form, which increased the Earth's albedo, making global temperatures fall even more, creating an icehouse Earth. We have another variable we will introduce here, the orbital cycle and wobble of the Earth. Gravitational forces from Jupiter, Saturn, the Sun, and the Moon distort the circular path the Earth takes around the Sun, causing the Earth to wobble irregularly over time, resulting in rhythmic or cyclic climate fluctuations. These fluctuations coincide with the 20 cycles of warming and cooling or glacial and interglacial stages observed within our current ice age. Some variations in the cycle have been observed, which we might all expect at this point since there are so many variables involved when it comes to climate fluctuations. But we have remained in this ice age as the ice sheets have never completely melted. Since I already had this slide prepared for another video I created, I thought it would be good to throw it in to provide a visual for this tectonic-driven climate change event. Tectonic forces pulled South America and Australia away from each other. The direction of the tectonic plate movement is shown by the orange arrows. As the continents drifted apart, the Drake and Tasmanian passages were open. This would result in a change from the ocean currents shown in this screen by the black wavy lines to the current pattern shown on this screen. The circumantarctic current still exists today and it circles Antarctica. It is a major reason for why Antarctica is so cold. The current caused ice sheets to form, which grew even bigger when carbon dioxide levels began to fall about 34 million years ago. I have one last example I would like to present. About 74,000 years ago, a supervolcanic eruption took place in Sumatra, Indonesia. The eruption of the Toba volcano takes the crown as the Earth's largest known explosive eruption. This eruption resulted in a severe global volcanic winter that lasted 6 to 10 years, contributed to a 1,000-year-long cooling episode, and is thought to have caused a genetic bottleneck in human evolution. This event took only 9 to 14 days to reach completion. Chemistry is different for different volcanoes. In the case of the Toba volcano, there were large volumes of sulfuric acid and sulfur dioxide that came along with the ash from this massive Plinian volcanic eruption. The sulfur dioxide would bond with water, creating a large concentration of acid rain droplets in the stratosphere, which are extremely effective at reflecting solar radiation. The droplets and the 3,000 cubic kilometers of volcanic ash would travel around the world, blocking out sunlight and causing temperatures to drop. Cold temperatures and low sunlight would kill off many plants and animals. Though this did not result in an extinction event, it drastically reduced evolving human populations. For a little perspective, this volcano released the energy of 1 million tons of explosives, 40 times more powerful than the most powerful hydrogen bomb ever built. It was 1,000 times more powerful than Krakatoa and 3,000 times more powerful than Mount St. Helens. The sonic boom would have been deafening. My objective during this presentation was to convey the complexities associated with climate change using some significant events that have happened in the Earth's past. And we only scratched the surface. I am not going to address the current climate change issue because I'm not here to form any opinions for you. Truly accurate models have not been developed that can explain all warming and cooling phenomena and all the effects associated with the latter, though models have come a long way. The evolution of planet Earth as a whole is complex. Changes in ocean chemistry, atmospheric chemistry, soil chemistry, flora, fauna, tectonics, topography, hydrology, and so much more all have or have had a part in climate change. There are many, many variables that affect or contribute to climate change. It is hard to find proxies for climate comparisons in a world that has never truly been the same. It is dynamic, and new variables are being introduced all the time. My 2 cents consist of the following. Make sure potential fixes here aren't making environmental or humanitarian issues elsewhere in the world. Just because you can't see it happen doesn't mean it's not happening. Think about some of the causes and effects we have gone over and think of any initiatives that would be cause for further climate change. Also, as is always the case, be cognizant of where your information is coming from and do your own research. There wasn't a piece of this presentation that was straightforward and didn't warrant further research. I would like to thank you for joining me on this climate change journey. We have several other distance learning videos that can be accessed by following the URL or scanning the QR code shown on the screen. Have a great day.